Hello everyone, my name is Aryan Thakur, and today I would like to explain how we can do fixed point real arithmetic in the C language using purely integers. Now, many of you must have already started with the MLFQS for Project 1 and may have quickly come to realize that certain variables like, well, the recent CPU variable or the load average variable are supposed to be floating point, but unfortunately, PintOS does not support floating point numbers. So we may have to find a way how to simulate calculations with floating point numbers or real numbers using purely integers. Now, this isn't something which is very tough. In fact, it's done a lot and it's known as the P.Q notation. In order to represent a floating point number using an integer, a 32-bit integer, we need to divide this 32-bit integer into a fractional part and an integer part. For all intents and purposes of PintOS and this video, we will be using the 17.14 notation. This means that the least significant 14 bits of a number, of a 32-bit integer, that is bit number 0 to bit number 13, would be used to represent the fractional part of a number. 17 bits, that is bit 14 to bit 30, are the new integer part of the number, and bit 31, which is the most significant bit, is just the regular sign bit. Now, how do you represent something like the number 1 in this notation? Normally, something like int x is equal to 1 would just mean that we keep the least significant bit 0 high and all the other bits low. But in this new notation, it is important to consider that bit number 0 to bit number 13 are just reserved for the fractional part of a number. And bit number 14 onwards is where the integer part of the number starts. Now the number 1 is just an integer, it has no fractional part. So in this notation, we keep the 14th bit high, which is the new LSB for integers, not for the fractional part. It's the new least significant bit for integers. So keeping this high is how we represent the number 1 in the 17.14 notation. A simple way of thinking about it is just to left shift by 14. Now, what exactly is this 14th bit high and all the other bit low in the C language? How would we see this as an integer? Well, this is just 2 raised to the power 14, which is 16,384. This is a very important constant, since to represent virtually any number in the 17.14 notation, we need to know this 16384 number. Now, why is that? Well, it's important to consider that any single number is itself multiplied by 1. For example, the number 3 is 3 into 1. The number 17 is 17 into 1. The number 3.133 is 3.133 into 1. Similarly, if we want to find the number 2 in the 17.14 notation, all we have to do is double 16384. If we want to find the number 0.5 in the 17.14 notation, all we have to do is half this 16384, since we already know that 16384 is the new number 1. So we can virtually convert any normal number into this 17.14 notation by just multiplying it by 16384. 16384, I know I've said it a lot, is a constant, and it's denoted by, it's actually the small f, but well, it's a constant, so I just like to keep it capital. Converting a normal number into the 17.14 notation is quite simple, but well, there are some intricacies when we want to convert back into a regular number. Now, conversion back into a regular number is, of course, well, right shifting by 14 or dividing a 17.14 number by 16384. However, due to the way division is structured in the C language itself, division always rounds off to the nearest zero. For example, if a division result is 1.999, it would round off to 1 and not to 2. Now, there's a simple workaround this, since to convert anything from a 17.14 notation to a regular notation, we would divide by 16384. So even something which is just under 16384 is double, it would be converted to the number 1, when it should be, well, converted to the double, which is 2. Anyways, there's a quick fix around this, And that is adding f by 2 to a positive number before converting it back to a regular number by dividing it by f, or subtracting f by 2 from a negative number before we divide it by f. And well, this simple workaround does work wonders. And there is a simple explanation I could give you on why this works. Well, simply, for example, let's take the number 1.6. Now, if we do want to convert it, for example, 1.6 in this 17.14 notation would be 1.6 into 16384, which I'll quickly get the answer. And that is 26214 approximately. 26214. Now this 26214, if we do divide it by 16384, we would of course get something which is approximately 1.6, which would of course be rounded off to 1. However, if we do add f by 2 to this, so f by 2 is, well, 8192, we would get something which is closer to the ranges of 34,000. And that divided by 16384 is, well, clearly 2. So this is a simple example to show why adding f by 2 to a number would really help in conversion back into a regular integer. Now, these conversions are pretty important, and simple operations like addition and subtraction, if we have two numbers in the same notation, I mean, is pretty simple. For example, two numbers in the 17.14 notation can just be added, and we would get the correct 17.14 notation for its sum, or subtracting would have the same result. However, do not forget to convert into the correct notation. For example, never add something which is in the 17.14 notation and add that to a regular notation, since that would give an absolutely absurd answer. Now, multiplying and dividing with such numbers is slightly different. For example, let's take this this question, 59 by 60 into 59 by 60. Now, this would be, of course, these numbers are approximately 1. They're just under 1. Even this number is just under 1. So we expect to have the result just under 1, right? Something like if 16384 in this notation is 1, and we should have the number in this 17.14 notation, something just under 16384. However, 59 by 60 in this notation is 161111, which is something 16111, which is something we expect. And multiplying 16111 by 16111 would give us something which is some absurdly big number, something in the ranges of 259 million, which definitely isn't any way close to 1, even in the 17.14 notation. This is important to note, and whenever we do multiplication of such 17.14 numbers, we need to always shift back by 14 bits. That is basically dividing it once again by 16384 to get the correct result. And yeah, this would give us basically 15842, which is 0.97, which is the correct answer we want. So always remember, when we are multiplying two numbers in the 17.14 notation, it is very essential that we shift it back by, right shift the bits by 14 to get the correct result. Similarly, for division, we need to left shift by 14 to get the correct result. It is also worth noting that in some cases, although like 16111 times 16111, even 259 million does fit in the prescribed range for an integer part. But something like 64 times 64, which would be something like 64 into 2 raised to the power 14 into 64 into 2 raised to the power 14, will definitely overflow your 32-bit integer completely, since we are using 32-bit integers to split between an integer part and a fractional part. So when we multiply even something like 64 times 64, it will definitely overflow your 32-bit limit. And to combat that, it is very important that multiplying is done in a 64-bit range, that's in 6040. So always remember to keep a multiplication going on in the 64-bit integers. And once we convert it back, we could convert it back to a 32-bit integer. I have prepared an example, a function I have defined for multiplying 17.14 numbers, and I will get to that very soon. Um, so if you do see the sample solution, I don't mean the sample solution. If you do see the sample required lines of code, which is there in the documentation of PintOS, it's they do show a new header file known as fixedpoint.h. They do not show, however, any fixedpoint.c file, and it is quite important to note that it is possible to fit in all of these functions which you would like to make, something like multiplying two 17.14 numbers or conversion. All of this could indeed fit in a header file by making these functions into external inline functions or just defining them as a whole. So let's go on to this fixedpoint.h. And here is a small file I've created to just show how you could fit in everything in just a header file. So I've defined a function in which I convert a regular number into a 16.14 notation. That is, I define 2 real and n into f. Of course, I've forgotten to define what f is. So let me just do that. Define f16384. Over here, I've kept an external inline function, which is multiplying two real numbers, so multiplying two 17.14 numbers. And this simply is, as I mentioned before, converting the first number into a 64-bit integer, multiplying it, having this overflow contained in a 64-bit integer, then dividing it back by f, since we have to write shift 14 bits to the right. And eventually we should have converted it back into a 32-bit integer, and we are good to go. So yeah, that basically is all I have to say about fixed point arithmetic in C language and in PintOS. And yeah, I wish you guys all the best for your projects.